All right, good evening and welcome to Master Talker online class. In today's video, we'll be talking about latent heat. All right, now this is our second video on heat energy. Okay, so if you have not watched the first one, please watch that before this one. And then if today is your first day of watching our video, please subscribe. Okay, now latent heat is defined as, in fact, latent means hidden. Hidden. So latent heat simply means hidden heat. If I call it hidden heat, hidden. Yes, hidden heat. Okay, latent means heating. Okay, they say latent heat is defined as the quantity of heat energy needed to change the state of a substance at constant temperature. In fact, if an ice, for example, we have three states of matter. Okay, we have the solid state, we have the solid, the liquid, the liquid spelling, and then the gas. Okay, now if you are changing from solid, for example, maybe water that is at 0 degrees Celsius, okay, want to change from water now to liquid, okay, and maintain the same 0 degrees Celsius, it doesn't change temperature, then we call the heat that is required to transform this thing from solid to liquid as latent heat. In fact, to make it specific, you call it latent heat of fusion. Latent heat of fusion. Okay, then maybe water that is at 100 degrees Celsius, okay, changes to a steam, to gas, and maintain the same 100 degrees Celsius. We call that heat that requires to do that thing without a change in temperature. We call it latent heat. But we call it what? To be specific, latent heat of vaporization. So we have two types of latent heat. We have latent heat of fusion and latent heat of vaporization. So from what they say here, they say that, note, latent heat is also called hidden heat. Yes, I said that. This is because the latent heat supplied to a body does not manifest in terms of temperature rise and hence cannot be detected by a thermometer. Yes, latent heat, we cannot use thermometer to measure it. In fact, once you put thermometer and you're talking about latent, it will not show anything. It is a hidden heat. All right. So a question one year WAEC said that we should explain using kinetic theory of matter why ice of 0 degrees Celsius can change to water at the same temperature. Okay, and the answer is because of latent heat. So they say here the answer: ice at 0 degrees Celsius can change to water at the same temperature of 0 degrees Celsius, even though heat is supplied to it. This is because all the heat energy supplied at this point is completely absorbed by the ice, only to break the intermolecular forces of attraction holding it in its solid state to form a liquid, that is water. Okay, by the same token, water at 100 degrees Celsius can be converted to steam at the same temperature. This is because the heat supplied can only be used to energize the water molecule, so that the increase in their kinetic energy will enable them escape from the surface of the liquid, that is vaporization. Any further heating when the boiling point has reached cannot rise the temperature above. This boiling point cannot above the boiling point, but can only impact more kinetic energy to the molecule. Hence, evaporation is taking place. In general, the temperature of the substance remain constant during phase transition. And phase transition means the change of state. Okay, so that is what. So exactly what I explained here. What did I explain? That if an ice from here can change from solid to liquid without a change in temperature, what happened there is what? Latent heat of fusion. It is called latent heat of fusion. Okay, so mathematically we say that what? Latent heat, let's represent latent heat with Q. Latent heat is directly proportional to mass. Okay, then if you remove proportionality sign, you have that Q is equal to what? Lm or ml. OP LMN. So Lm, we use Lm to know that according to your alphabet. LMN, Lm where my Q is called the latent heat. Latent heat. And heat is measured, is an energy, so it is measured in joule. And my M is what? The mass, measured in what? In kg. And then my L is called the specific latent heat. The specific latent heat. Specific latent heat. So measured in joule per kg. Joule per kg. Okay. So that is that. So now let's talk about specific latent heat. Okay. I told you we have two types of specific latent heat. We have the specific latent heat of fusion and specific latent heat of vaporization. Okay. Specific latent heat of fusion and specific latent heat of vaporization. They say that the specific latent heat of fusion of ice is defined as the quantity of energy required to convert a unit mass of ice, that is solid, at 0 degree temperature to water, liquid, without any change in temperature. I have told you that. Why the specific latent heat of vaporization is the quantity of heat, energy needed to convert a unit mass of water at 100 degrees Celsius to steam at the same temperature. That said, when ice is heated from 0 degrees Celsius until it boils away, the total heat energy required from this process can be obtained using the trend shown below. And look at the trend. They say that ice changing to water, okay, and then changing to, and what happened here, that water is at 0 degrees Celsius, okay, then changing to another water again, but this time around this water is at 100 degrees Celsius, then changing to steam, and here is another 100 degrees Celsius. Okay, so at ice was 0 degrees Celsius. So what do I have here? What I have here is melting. That is fusion of ice. What we have here is boiling, and in boiling I have what, in fact, this process is what, ML. This one, there's a change in temperature, so here is what, MC, change in temperature. Here there is no change in temperature, so here is equally ML. So what happened here is vaporization. Vaporization. And is what we have there is what, latent heat of vaporization. Okay, we can say that what, Q, the total heat, is what, ML plus MC, change in temperature, plus ML again. Okay, so that is that. That's it. Where M is the mass in each of the case, the mass of ice. Okay, M is the mass of the ice that did all this transformation. Where L, under the melting, and blah blah blah. That is that. Then for ice at minus 10 degrees Celsius to change to steam at 100 degrees Celsius, we have this. Okay. So from this, let us now solve calculation. Since we have known that Q is equal to what? ML plus MC, change in temperature, plus what? My so this is, I hope you remember what Q is. Q is what? Your latent heat. Your latent heat is equal to what? ML plus MC, change in temperature, plus this. Why do we have this? I will show you why we have that. So let us solve calculation to illustrate what we have done so far. Okay, but you should know that there are two types of specific latent heat. The first one is what? The specific latent heat of fusion, and the specific latent heat of what? Vaporization. Question number 1 said how much heat is required? How much heat is required to convert 20 gram of ice at 0 degrees Celsius to water at the same temperature? Now, since there is no temperature, they now say you should take that the specific latent heat of ice to be 336 joule per gram. Okay, joule per gram. Okay, since they gave it to us in joule per gram, we should leave our answer in gram as well. So solution, what do we have? What do we have here? The first thing they gave us is the mass. The mass is what? 20 gram. Okay, and I will have our L, the specific latent heat, as what? 336 joule per gram. Okay, and I know that my Q is equal to what? ML, which is what? 20 times 336, which will give you what? 20 times 336 will give you 6720 joules. So that is my what? My latent heat. The latent heat. Question number 1 done. Question number 2, very simple. Question number 2 says 500 gram of water at 10 degrees Celsius is completely converted to ice at 0 degrees Celsius by extracting 188,000 joules of heat from it. Okay, then I say if the specific heat capacity of water is 4,200 joule per kg per Kelvin, then I say calculate the specific latent heat of fusion of ice. Okay, now what you need to know here is that solution, that your Q is equal to what? MC change in temperature plus what? ML. That is what you need to know here, because it is changing normally. The first thing that changed, there was a change in temperature, while the other one, there is no change in temperature. So these are the two things you need to know here. Okay, like they did. Look what they did. The first one was from here, from 10 degrees Celsius to what? To water at 0 degrees Celsius to another water again at what? 0 degrees Celsius. Okay, so that is what happened. So this one is now ice. So the last one was ice. It was moved from here to here. So that is why we have that formula. So what do we have? Our Q is what? My 188,000 joules. Okay, my M, the mass is what? 500 gram, which is what? 0.5 kg. Okay, my C, even if we are not given, we know is 4,200 joule per kg per Kelvin. Okay, and then we're asked to get our L. Then we know that the theta there, change in theta here is from 10 to 0. That is what? 10 minus 0, which is what? 10 degrees Celsius. Okay, that is my change in temperature there. Okay, from 10 to 0. So that is that. So we now have a formula that says that what? From here, our Q is equal to MC change in temperature plus what? Our ML. That is 18,800 is equal to my M. My M is 0.5 times my C is 4,200 times my change in temperature, I got 10, plus my M is still 0.5 times my L that I'm looking for. So this is 18,800 is equal to multiply 42,000 times 0.5. So I have 21,000 plus 0.5 L. So subtract 0.5 L is equal to 188,000 minus 21,000. So 0.5 L is equal to minus 18,800. So I have 167,000. So my L will now be 167,000 divided by 0.5. So what do you have? Divided by 0.5. I have 334,000 joule per kg. Okay, that is my latent heat, joule per kg. All right, very simple question. Question number 3. Right, question number 3. Question number 3 says calculate the heat energy required to vaporize completely 20 grams of water initially at 60 degrees Celsius. Initially at 60 degrees Celsius. Okay, now solution. For vaporization, if the water H2O should be converted from 60, okay, it will start boiling H2O again. That is 100 degrees Celsius. It will start boiling. Then it will now vaporize at the same thing without what? Without change in temperature. So what we are going to have here, you know that here is what? Heat loss. I hope you know here is heat loss. It's not heat gain. Okay, I think it's heat gain. It's heat gain. So final minus initial. But the first one we did was heat loss. That's why we did initial minus final. Okay, so my Q will now be what? MC change in temperature plus what? My ML. So that is that. My MC is what? What they say we should calculate? Heat energy required. Okay, my M is what? My M is what? 20 gram, which is what? 0.02 kg. So I have 0.02 times my C, specific heat capacity of water is 4,200 times my change in temperature is what? From 100 minus 60. Okay, plus my M there is another 0.02 times my latent heat, my specific latent heat of water is we should know it, please. Okay, they gave it to us here anyway. They said it's 2260. Okay, they say take the latent heat of vaporization of water to be where is it? The latent heat of vaporization of water to be 226,1,2,3,4. Okay, that's what they gave us. So we have 226,1,2,3,4. Okay, so that is, they say take the latent heat of vaporization. Okay, so that is that. So what do we have now? If you multiply everything here, you'll be having if you are 100 minus 60 will give you 40. So I have 40 times 0.02 times 4200. So I have 3360 plus, do the same thing here, 226,1,2,3,4 times 0.02. I have 45200. So if you add plus 3360, so I'm going to have 48560 joules. 48560 joules. Okay, I hope I didn't make mistake. 45200 plus 3360. Yes, 4856. Okay, so that is that for that. The next question, question number 4. Question number 4. Question number 4 said how much heat energy is required? How much heat energy is required to convert 2 kg of ice initially at minus 10 degrees Celsius to steam? Okay, initially to steam. Now solution. Now don't forget that this is from minus 10 degrees Celsius, okay, to what? 0 degrees Celsius. Then it is now at ice. Then from that ice to water again, but that water should be at 0 degrees Celsius. Then from that water will now enter to what is it called? Watch you. From minus this to 0. The 0 is ice. From ice to water. Okay, from that water it will start boiling. From boiling it will now move to steam at the same 100 degrees Celsius. So what we have here, there is a change in temperature here. So there's a change in temperature. I'm going to have the Q now will now be what? MC change in temperature plus ML from here to here. Here to here is ML. Here to here is another MC change in temperature plus the final one ML again. So that is the four of them we have now. This is the four of them we have. Okay? So that is that. So what do we have now? We are going to have that our Q is equal to my M. My M is 2 kg. 2 times my C, specific heat capacity of water, is always 4,200 plus my change in temperature. Is this heat gain or heat loss? That is another question you ask. From minus, it will gain energy. That is why it became this. So it is heat gain. So if it is heat gain, it's going to be 0 minus minus 10. Okay? 0 minus minus 10. Did I get that? Yeah, that is very correct. Okay? Plus my ML. My M here is, let me clean here. My M does not change. My M is equally my 2 times my L is 4 to they gave it to us anyway, but we need to know it to 226, then 4 zeros. 226, 1, 2, 3, 4. That is my L. It doesn't change. Plus my M again, 2 times my C, 4200. It doesn't change. Then, if you look at this place, this one, is it heat gain or heat loss? It's still gain because it's from 0 to 100. It's still gain. So I'm going to have 100 minus 0. Okay, plus then the last part, my M is 2 times my L again. My L again is 226, 1, 2, 3, 4. So what do we have? We now have that my Q is equal to 0 plus this is 10. So I'm going to have 2 times 4200 times 10. I'm going to have 84. 84. How many zeros? 1, 2, 3, 4. Plus I have 226. 226. 1, 2, 3, 4 times 2. I'm going to have 452. 1, 2, 3, 4 plus 2 times 4200 times 100. I have 84, 1, 2, 3, 4. Okay? This one is 1, 2, 3. This is 3. Okay? This is 2 times 4200 times 10. Yes, 3. Why this one is 4? Okay? Plus this one is 10 again. 4, 5, 2, 1, 2, 3, 4. Okay, so let us add. Plus, okay, I have 8400 plus 840000 4 plus 452 1, 2, 3, 4 plus 452 1, 2, 3, 4. So I have 9964123 in joules. So that is that for that. Okay. So that is the heat required. The heat required 2 times. Okay. That is that. But the question here, oh, they gave us different things anyways. They gave us the specific heat capacity of ice and the rest. So, but this is the formula to use anyways. This is the formula to use, and then I did not see where they gave those things. So, but this is exactly what to do if you are not giving the specific heat capacity of each of them separately. Okay, but I know it's supposed to be different. That's the mistake I made anyways. Question number 5. Question number 5 said all the heat generated, all the heat generated by a current of 2 ampere passes, okay, passing through a 6 ohm resistor for 25 seconds. For 25 seconds is used to evaporate 5 gram of a liquid at its boiling point. Then I say, what is the specific latent heat of the liquid? Okay, solution. So what do we do? Don't forget that electric energy is equal to heat energy. Electric energy is equal to what? Heat energy. So, but in this one, what I have is my IR. So I know that my electric energy is equal to what? IVT. Don't forget. But I'm not giving V. I know that it's equal to V is equal to IR. So if I now change it, which is equal to what? ML. Why am I using ML? Because it is latent heat they are asking us. There is no change in temperature. Okay. So if I now put it, I'm going to have I squared R. You now put my T is equal to my ML. So they're asking me L. My L will now be I squared RT over my M, which is what? My I is 2. So 2 squared, my current is 2, times my resistor 6 ohms, 6, times my time 25 seconds, 25 seconds all over. My mass is 5 gram, and 5 gram is 0.005. 1, 2, 3. That is 0.005. So if you do that, you're going to have 4 times 6 times 25. 4 times 6 times 25. Then divided by 0.123. So I have my L is now 12,000 in joule per kg. In joule per kg. So that is that. A very simple question. Joule per kV. Okay. Yes. So 120 kilojoule per kg. If you want to put it in kilojoule per kV. Okay. Question number 6. We are moving. Question number 6 said 80% of heat supplied to a 30-gram block of ice at 0 degrees Celsius completely melt into water at 0 degrees Celsius. Calculate the total energy supplied. Then I said that the specific latent heat of ice is equal to 336 joule per gram. Okay. So now solution. We know that we are simply changing from 0 to 0 degrees Celsius to 0 degrees Celsius. That's the only thing we are changing. So we should know that our Q now is equal to what? What they say, we should calculate the total energy. So our Q is equal to what? ML plus ML. Is it? or just ml. It's just ml because it's simply one from here to here is ml. So what do we have? My m is 30 times my l is 336. So if you are going to multiply that, you're going to have 30 times 336. So I have 10080 joules. But what they say that it is what? 80% of this heat supplied to this block of ice is completely, so 80% is the one supplied. So 80% of that will now be, so the total heat supplied is 80% of this one. So the total heat is equal to what? 80% of 10080, which is what? 80 divided by 100 times 10080. So what do you have? That is 8084 in joules. 8084 in joules. All right. So we're going to solve just 2 more questions and then we are good to go. Let me check my time. Okay, 31. Okay, they said a piece of copper, Cu, a piece of copper of mass 120 gram is heated in an enclosure, okay, in an enclosure to a temperature of 125 degrees Celsius. Okay, then I said it is then taken out of the enclosure and held in air for half a minute and dropped carefully into a copper calorimeter, okay, of mass 105 gram, containing 200 gram of water at 20 degrees Celsius, full stop. Okay, then I said the temperature of the water rises to 25 degrees Celsius. Then say calculate the rate of which heat is being lost for the piece of copper when it is held in air. Solution. Okay, all right. They said that what? A piece of copper of mass. So let's take the mass of the copper. The mass of the copper is M1. Let's use the copper as 1. So the mass of the copper is 120 gram. Okay. 120 gram. Let me convert it, which is what? 0.12 kg. Okay. Then is heated. Then the temperature T1 is 125 degrees Celsius. Then it is taken out of an enclosure and held for some minutes. But I know that the specific latent heat of that copper is 400 joule per kg per Kelvin. Okay, it doesn't change. Okay, so we now have that is held for some minutes and dropped carefully into copper calorimeter. So my MO2, mass of the calorimeter, is 105 gram. Okay, the temperature of that calorimeter T2 is what? The temperature is 20. They said, huh? Into a calorimeter of mass, this containing, okay, the mass of the water MO3 is equal to what? 200 gram. Okay, sorry, and this one is equal to 0.105 kg. Okay, and 200 gram, which is what? 0.2 kg. Okay, and the temperature of that water, the temperature of the water was at 20 degrees Celsius, but the temperature of this calorimeter is the one reading so yes, it's still the temperature of the water, which is what? 20 degrees Celsius. But the new temperature, theta 4, will now be what? 25 degrees Celsius. That is, when they dropped it, it now raise, now rise. Okay, so we have everything we want. So we know that heat energy is equal to heat gained is equal to heat loss. The heat gained is equal to the heat loss. Okay, so what do we have? Heat gained is equal to what? Heat loss. Now, the only one that gained heat, or let me say heat loss, because the only one that lost is just one person. Heat loss is equal to heat gain. So we have that what? M1 C1 is only one that lost heat. So since it is lost, it's supposed to be theta 4 minus theta 1. So what is going to be theta 1 minus theta 4? Okay? Because it is loss. So is equal to heat gain. The calorimeter gained. So I'm going to have M1 C1 into theta 4 minus theta 2 because it is gained. Plus, sorry, 2 here. So MO3 C3 in bracket of what? Theta what? What am I saying? Theta 4 minus theta 3. Okay? So let us check that. That is normally if you ignore anything. But I want to first of all get heat loss. Let's get it one after the other. Heat loss is equal to M1 C1 theta 1 minus theta 4. Let's see what it will give us. My M1 is equal to what? 0.12. 0.12 times my C1. My C1 is 400. Okay, in bracket of theta 1 is 125 minus theta 4 is 25. So what do I have now? So I'm going to have 0.0.12, okay, plus, sorry, times 100 times 400. So I'm going to have 4800 joules. This is my heat loss. Then let's talk about heat gained. Heat gained. Now, heat gained is the both of them is supposed to be M2C2 into theta 4 minus theta 2 plus M3C3 into theta 4 minus theta 3. Okay, so what do I have? My M2, the mass of the calorimeter, which is 0.105 times 400, because the calorimeter is made with copper, in bracket of what? 25 minus theta 2. Where is my theta 2? 20. Okay, plus my MO3, the mass of the water, that is 0.2 times specific heat capacity of water is 4200 in bracket of 25 minus 20 again. Okay, so what do I have? Let me press everything. I'm going to have 25 minus 20 will give you 5. 5 times 400 times 0.105. I'm going to have 210 plus 5 times 4200 plus 0.2. I have 0.2 times 4200 times 5. I have 4200. Okay, so if you now add plus 210, you now have 4410. Now in joules, if you look at this on a normal, they are supposed to be equal, but what happened when let's know the amount of energy in air. The amount of energy in air should be this one minus this one, because they are supposed to be equal. So the amount of energy in air, the amount of energy in air, energy in air, energy lost to air, heat energy lost in air will now be what? 4800 minus 4410. So what do you have? You have 390 joules. Okay, 390 joules. So then I say we should calculate what? The rate of the power is the energy over time. That is half a minute. Okay, what do they say? Calculate the rate of which the energy. Okay, the rate of energy is power. Don't forget that rate of energy is power. So what do we have? The rate of energy means power. So the rate of energy is equal to energy over what? Over time. So what is the energy? 390 was lost. And how many minutes? 1 minute. And half a minute. Half a minute is 30 seconds. 30 seconds. So what do you have? Half a minute is 30 seconds. So what do you have? 390 divided by 30. So I have 13. That is 13 what? Watts or joule per sec. Either joule per sec or watt. Anyone you like. 13 joule per sec or watts. So it's a very simple question. It's a very simple question. Okay? So the next question, question number 8. Question number 8 said, when 100 gram of liquid L1 at 780 degrees Celsius was mixed with X gram of liquid L2 at 50 degrees Celsius. Then I say the final temperature was 660 degrees Celsius. Then I say given the specific heat capacity, the specific heat capacity of L2 is half of L1, find X. A very simple question again. So what do we do? To find F, what do we do? To find our X, what do we do? So the first mass M1 is what? 100 gram, which is same as what? 0.1 kg. Okay? The second mass M2 is equal to what? X in gram, which is okay, let me leave them in gram. It can be 0.001x in kg if you want, but let me just leave everything in gram, no problem. I will still convert to kg. Okay, so then I say that that this C1, my C1 is the specific heat capacity of L1 is half of L2. They say that the specific heat capacity of L2 is half of L1. That is C2 is equal to what? 1 over 2 C1. So therefore, C1 is equal to 2 C2. So C1 is equal to 2 C2. Then C2 is equal to C2. So I've gotten that. Okay. So I need the temperature. Theta 1 is what? It was at 78 degrees Celsius. Okay. And my theta 2 is at what? As 50 degrees Celsius. Then my theta 3 is now what? 66 degrees Celsius. So if you look at these two, this is heat loss. Okay. So I will tell them that heat gained is equal to heat loss. Heat gained is equal to what? Heat loss. Okay. So for heat gain, who gained? This person gained. Okay, the one with smaller temperature gained. So I'm going to have my M2 C2 theta 3 minus theta 2 because it is gained is equal to what? M1 C1 theta 1 minus theta 3 because it is loss. Okay, so what do I have? My M2 is 100. My C2 is still my C2 in bracket of what? 66 minus 50 is equal to what? My x. This one is my x. My C1 is equal to what? Times 2C1. Okay, sorry, 2C2. Because my C1 is equal to 2C2. The way I got it is that they say that C2 is equal to half C1. So if you cross multiply, see that C1 is 2C2. Okay, then times my theta 1 is 78 minus what? 66. So what do I have? C2 will cancel C2. So what do I have now? 66 minus 50. 16 times 100. I have 1600 is equal to 78 minus 66. I have 12. 12 times 2 times x. So what do I have? 24x. So my x will now be 1600 divided by 24. So what do I have? 1600 divided by my last answer. So I have 16.7 gram. So the answer is what? 16.7 gram. So if you want to convert to kilogram, you are going to have divide by 1000. I have 0.16 gram. So that is that for that. That is that for that. Okay. Okay. So the next question. I hope there is no mistake anywhere. You can check out for mistake. 100 gram. So that is that. Very simple. So question number 9. Question number 9. Question number 9 is going to be your assignment. So you tell me the answer at the comment section. So question number 9 said how many grams of water at 170 degrees Celsius must be added to 42 gram of ice, okay, at 0 degrees Celsius to melt the ice completely. Okay, they now say you should take the latent heat of fusion of ice. They say take the specific latent heat of ice as 3.4 times 10 raised to power 5 joule per kg, and the specific heat capacity of water, the specific heat capacity of water as 4200 joule per kg per Kelvin. So thank you very much for watching. Please subscribe. Bye bye.